Monoidal categories and their representations, lecture 20, problem session. Problem 1. Let C be a monoidal category with a symmetric braiding sigma. Define the notion of a Hopf algebra object in C, it's also known as a Hopf monoid, and show that the identity object I in C has the natural structure of a Hopf algebra object. Solution. We just follow the definition of the Hopf algebra. So we define a Hopf algebra object in C as a tuple which consists of 6 entries. The first one is H, and this is an object in C. The second one, denoted by bold M, is a morphism from H tensor H to H. So this is our analog of multiplication. The third one, eta, is a morphism from the identity to H. This is our analog of a unit. Then we have delta, which is a morphism from H to H tensor H. So this is our analog of comultiplication. Then we have epsilon, which is a morphism from H to the identity. This is our analog of a counit. And we have omega, which is a morphism from H to H. This is our analog of an antipode. And we demand that these data satisfy the following commutative diagrams. So now we start list of all the commutative diagrams associated with a Hopf algebra object in a monoidal category. So first of all, the multiplication should be commutative. So starting from H tensor H, the two bracketings are connected by the associator alpha. Then we can go to H in two different ways, by multiplying the first two components or the last two components, and then multiplying the outcome going to H. So this diagram should commute. Similarly, the multiplication should be unital. In other words, starting from the identity tensor H, there is a canonical map lambda to H on the one hand. Alternatively, we can apply eta to the first component to go to H tensor H and then multiply. This diagram should commute, and a similar diagram with I being on the right-hand side, which uses rho, also should commute. Similar to the associativity of multiplication, we have co-associativity of comultiplication. So this is just the diagram. We take the associativity of multiplication, reverse the arrows, and write now the commultiplication instead of multiplication, and we have a similar diagram. This diagram should commute. And also, of course, the commultiplication should be counital. So we have the two counitality diagrams. Starting from H, we can go by delta to H tensor H. Then we can apply epsilon in the first argument to go to the identity tensor H. And then we have the canonical map lambda back to H. So this diagram should commute, and similarly for the second argument using rho. So these are the associativity and unitality of the multiplication and the co-associativity and co-unitality of the commultiplication. Next, there are several diagrams which can be interpreted as compatibility of the multiplication and the commultiplication. So the first diagram says that starting from the identity and applying the unit and then counit should give the identity map on the identity. The next two compatibility diagrams now involve multiplication and commultiplication respectively. The first one essentially says that the counit epsilon intertwines the multiplication on H with the canonical map lambda, which is rho or which is iota, on the identity. And the second diagram says the same thing when we, instead of the multiplication, have the commultiplication. Instead of epsilon, we take eta, and instead of lambda or rho, we take the inverses. So they coincide. So these are the second and the third compatibility diagrams. And we have one more compatibility diagram, which essentially says that multiplication is a homomorphism of coalgebras and commultiplication is a homomorphism of algebras. So starting from H tensor H, we can multiply to H and then co-multiply back to H tensor H. Alternatively, we can co-multiply on both components to go to H tensor H, tensor H tensor H. Then we use the associator to rearrange the brackets so that we have in the middle H tensor H, to which we apply our symmetric braid in sigma. So this is the place where the symmetric braid in sigma is used. So this is important for this definition. And then we again rearrange the bracket so that we can multiply the first two components and the second two components to go to H tensor H. So this is the force compatibility diagram. And finally, we also have the antipode diagram, where we start from H. We use the co-unit and then unit to go back to H. And alternatively, we co-multiply to H tensor H, apply the antipode on one of the components, and then multiply. So we can choose the first component or the second component, and this gives us this diagram with three different passes from H to H. These three passes should coincide. And this completes the definition of a notion of a Hopf algebra object in a monoidal category. Now, the last part of the problem, we need to check that the identity object has the natural structure of a Hopf algebra object. So for the identity, there are not that many choices for our structure maps. At the multiplication, we should take our lambda, which is the same as rho, which is the same as iota. For the unit map, we just take the identity. For the co-multiplication, we should take the inverse of iota. And for the co-unit map, we take the identity. And for the antipode, we also take the identity. So now we have to check that all our diagrams listed on the previous slides commute. So the associativity of the multiplication and the unitality of the multiplication for the identity, these were checked during the lectures. And similarly, one does co-associativity and the co-unitality. So if we look at the first three compatibility diagrams, they are almost tautological. So our H is identity and eta and epsilon are the identities. So the first diagram is absolutely obvious. And then these two diagrams, our multiplication is lambda and epsilon is the identity. So this is a tautological diagram and this is just the inverse of this one. So the first three compatibility diagrams for the identity are really trivial. So the only interesting things to prove are the last compatibility diagram, the big one, and the antipode diagram. So for the big compatibility diagram, so here it is repeated now with H substituted by the identity. And if we look at this diagram, then all maps which we have in this diagram are structural maps from our symmetric monoidal category, except for this sigma appearing here. So if we can prove that this sigma is the identity, then the commutativity of this diagram follows directly from the coherence theorem. And we will check that sigma for the identity is actually the identity on the next slide. So this establishes this last compatibility diagram. And the antipode diagram is really easy. So in the middle, we just have the identity map from the identity to the identity. And here, the two other ways, our co-multiplication is the inverse of iota. Then we have the identity in the middle. And then the multiplication is iota. Of course, iota after the inverse is the identity map. So the antipode diagram is really clear. So to complete the proof, we just need to prove that our symmetric braid in sigma, when restricted to the identity object, is given by the identity map. Okay, let's prove this. Recall that there was a lemma in lecture 8 where we established that any braiding, not necessarily symmetric, any braiding is compatible with uniters in the sense that for any object x, the following diagram commutes. So identity tensor x, we use the braiding to go to x tensor identity, and then from the first object we have the left unitor to x, from the second object we have the right unitor to x. This diagram commutes. So now if we take x to be given by the identity, then lambda is equal to rho, and they both are isomorphisms. This means that sigma must be the identity map because of the commutativity of this diagram, because lambda is equal to rho after sigma. So if we multiply this on the left with the inverse of lambda, which is the same as the inverse of rho, we get that sigma is the identity. And this completes problem 1. Problem 2. For a complex number q, consider the corresponding complex quantum plane, which is the associative unital algebra, denoted by the capital Q with this lower index lowercase q, and it is defined at the algebra with two generators x and y, and one relation xy is equal to qyx. The assignment is to show that this quantum plane is a Hopf algebra with respect to the following structure maps. So we have the commultiplication delta, which sends y to y tensor y, and x to y tensor x plus x tensor y. Our counit epsilon sends x to 0 and y to 1, and our antipode omega sends y to y inverse and x to minus y inverse x y inverse. So we don't need to define the multiplication and the unit because we start originally from an associative and unital algebra, so the multiplication and the unit, they are already defined. Solution. So we need to check that all the diagrams in the definition of a Hopf algebra commutes. So first, let us note that our quantum plane is generated by two elements, x and y, and here we define our commultiplication, counit, and antipode on these generators. We know that if this is a Hopf algebra, then the commultiplication, counit, and antipode are either homomorphisms or anti-homomorphisms, and so the fact that they are defined on the generators defines them uniquely. So if we will check all the conditions for the generators, everything will work out. So let us check all the conditions for all the structure maps. To start with, the co-associativity of the commultiplication when applied to x. So if we start with x and first do delta and then delta tensor the identity, this is delta tensor the identity applied to y tensor x plus x tensor y. So we take this formula. And now in the first component, delta y is y tensor x. So this is delta tensor 1 applied to the first element. And on the second element, we should apply delta to x, so we will get y tensor x tensor y plus x tensor y tensor y. So this is the outcome. And similar computation where we swap the identity and delta, we get identity tensor delta applied to y tensor x plus x tensor y. One can see that this element is invariant under the usual symmetrical braiding, and the symmetrical braiding, of course, will swap delta and the identity, so it's no surprise that the outcome is exactly as in the previous computation. So this checks the co-associativity when applied to x. The co-associativity when applied to y is obvious because the formula is very easy, and in both cases, one will just get y tensor y tensor y. So this checks the co-associativity of our co-multiplication. So we have two versions of the co-unitality of our co-multiplication. Let's again check them on the generators. So first, epsilon tensor ID after delta applied to x. So this is epsilon tensor ID applied to y tensor x plus x tensor y. Epsilon kills x, so we should only worry about the first summand. And in the first summand, epsilon of y is the identity, so we get 1 tensor x. And under the canonical map, which is given by the multiplication, this is sent to x. So x is sent to x. That's good. Similarly for y, so if we apply delta to y, we get y tensor y. And now we apply epsilon to the first component, so it becomes 1. And now again, if we multiply, we get y. So y is also sent to y. So we get the identity map, and this checks the first co-unitality. And the second co-unitality is similar. In the first computation, we need to have here identity tensor epsilon, and this will give us X tensor identity, and this under the multiplication is sent to X. And similarly for Y, we have identity tensor epsilon applied to Y tensor Y. This is equal to Y tensor the identity, and this is sent to Y under the multiplication. And this establishes the co-unitality. So the first compatibility diagram, that the unit and then the co-unit is the identity on the field K, is directly obvious from the definitions. And the other compatibility diagrams are easily checked by a similar direct computation. So a part of that is actually to check that delta is an algebra homomorphism. This we can check from the definitions immediately in the following way. So we need to check that delta applied to x and delta applied to y, when we multiply them, this is equal to q times delta y delta x. So our algebra, our quantum plane, is defined by one relation. So in order to check that delta is a homomorphism, we need to check that the images of our generators under delta satisfy the same relation. So let's check it. So the left-hand side here, using our formula, so delta of x is x tensor y plus y tensor x, and delta of y is y tensor y. And this is equal, when we just multiply in the tensor product, xy tensor y squared plus y squared tensor xy. The right-hand side, so if you forget q, delta of y times delta of x, we just swap the factors in the original product here, and when we multiply, we get yx tensor y squared plus y squared tensor yx. And now we can use that xy is q times yx, so this xy is q times this, and this xy is q times this. And this immediately gives us the necessary relation. So the antipode diagram, so this is the antipode diagram in our case. And again, let us check it for the generators. For x, the middle pass is 0 because epsilon sends x to 0. So the middle pass is 0. Let's do the upper pass. The commultiplication sends x to x tensor y plus y tensor x. So the antipode, it sends y here to y inverse, while this x is sent to minus y inverse x y inverse. And now when we multiply, in the first summand we get minus y inverse x, y inverse y. So this y inverse and this y. And in the second summand we get just plus y inverse x. So now we have a cancellation here, and using this minus sign we get 0. And similarly for the lower pass, we will have a similar expression, but now the cancellation of y and y inverse will appear on the left and in the second summand. So we get 0 again. So this diagram commutes when evaluated at x. And the evaluation at y is really easy. So the middle pass gives us 1 because epsilon sends y to 1, and then eta sends 1 to 1. And the upper pass is as follows. So y is sent to y tensor y. Applying the antipode on the first factor, we get y inverse tensor y, and when we multiply them, we get 1. And similarly for the lower pass. So this completes problem 2. Problem 3. For q equal to minus 1, show that c squared is a module over the quantum plane q corresponding to the value minus 1, where x and y act respectively via the following matrices. So x acts via the matrix 1, 0, 0, minus 1, and y acts via the matrix 0, 1, 1, 0. The assignment is to determine the lengths of the q minus 1 module given by the tensor product of this c squared with itself. Solution. To check that this is a module over q minus 1, let's compute the product of these matrices in both directions. So xy is equal to 0, 1, minus 1, 0, while yx is equal to 0, minus 1, 1, 0. So we see that xy is equal to minus yx, which is exactly the necessary relation in the algebra Q minus 1. So this proves that these matrices define on C squared the structure of a Q minus 1 module. So now if we take this module and tensor it with itself, the outcome has a standard basis consisting of the tensor products of the standard basis elements. We denote them v11, v12, v21, and v22. So Vij is EI tensor Ej, where I and j are from 1 and 2. So now the commultiplication delta in our algebra Q minus 1, it sends y to y tensor y. And therefore the action of y on the standard basis of the tensor product of C squared with itself is given by the following matrix. So v11, y sends e1 to e2 and e1 to e2. So v11 is sent to v22. So the first column is 0, 0, 0, 1. Similarly, v12, again, y sends e1 to e2 and e2 to e1. So v12 is sent to v21. So the second column is 0, 0, 1, 0, and similarly the third column is 0, 1, 0, 0, and the last one is 1, 0, 0, 0. So this is the matrix which represents the action of y on our tensor product. Now, for x, the commultiplication sends x to y tensor x plus x tensor y. So we should act by this element on the standard basis. So if you take v11, then y tensor x will send it to v21 because y just sends e1 to e2 and x does nothing to e1. And then x tensor y will send it to v12. So v11 is sent to v21 plus v12. So the first column of this matrix is 0, 1, 1, 0. Next, if you look at v12, then y tensor x will send it to minus v22. So y will move e1 to e2, but x applied to e2 is minus e2. So this gives us this minus sign. At the same time, x tensor y will send v12 to v11. So we'll have here 1 without the minus. And then we similarly obtain that the third column is the same as the second column in this matrix, and the last column is minus the first column. So the action of our algebra on this tensor product is given by these two matrices. If we try the vector 1, 0, 0, 1, we see that b times this vector gives us this vector back, while a kills it. This means that this vector generates a one-dimensional and hence simple submodule of our tensor product. Great. Next, let us try the vector u, which is 1, 0, 0, minus 1. So if we apply b, we see that b times u is minus u, because we have here 1 and here 1, which will swap them. And then au is equal to 0, 2, 2, 0. We denote this vector by w. And in turn, if we apply b to w, we will get w back, and aw is equal to 4 times u. So this means that u and w generate a two-dimensional submodule of our tensor product, but our two generators, u and w, of this submodule, they both are eigenvalues for b with different eigenvalues, and none of them is invariant under A. So this means that this two-dimensional submodule is actually simple. And if we factor out from our four-dimensional tensor product the two submodules, the one-dimensional computed on the previous slide and the two-dimensional, which we just computed, we will get a one-dimensional quotient that must be simple because it has dimension 1, and altogether this means that the length of our tensor product is 3. So we have one one-dimensional subquotient, one two-dimensional subquotient, and then one more one-dimensional subquotient. And this solves problem 3. Problem 4. Let K be a field of characteristic different from 2, and let D be the algebra of dual numbers over k. It's a quotient of the polynomial algebra in the variable x over k modulo the ideal given by x squared. Describe the cell structure and the cell modules for the monoidal category of all projective bimodules over the algebra D plus D. Solution. So the main difference with what we considered during the lectures is that the algebra D plus D is not connected. It's manifestly a direct sum of two non-zero algebras. So let us denote by D1 the first copy of D and by D2 the second copy of D in our algebra D plus D. And let us consider the monoidal category of all projective bimodules over D plus D. So this category has the following indecomposable objects. So first we have four indecomposable projective bimodules. D1 tensor over K with D1, D1 tensor over K with D2, D2 tensor over K with D1, and D2 tensor over K with D2. And also we have indecomposable non-projective bimodules because we have the identity object, which is usually not projective in this monoidal category. But here our algebra is not connected, so the identity object is decomposable. And it's a direct sum of D1 and D2. So exactly the identity object in our monoidal category decomposes as a direct sum of two bimodules. D1, the first copy of dual numbers, and D2, the second copy of dual numbers. Note that we have the following relations. So if we tensor over our algebra D plus D, D1 with D1, we will get D1. Because D2 kills everything, it will disappear. And we will get the tensor product of D1 with D1 over D1. If we tensor D1 over our algebra with D2, we will get 0. This is because D1 times D2 is 0. If we move over D1 to D2, we'll get 0. And similarly, D2 tensor product with D1 over our algebra is also 0. And similarly to the first line, D2 tensor product over our algebra with D2 is D2. This gives us the following cell structure. We have a singleton two-sided cell G1, which consists of D1. We have a singleton two-sided cell G2, which consists of D2. And we have a third two-sided cell J, which consists of all indecomposable projective bimodules. The two-sided order is as follows. J is greater than or equal to J1, and it is greater than or equal to J2, but J1 and J2 are not comparable in the two-sided order. So this is because of these two middle relations. Also, since J1 and J2 are singletons, they are at the same time left cells and right cells, while the big two-sided cell J splits into two left cells, the left cell L1, where the right component is fixed as D1 and the left component is either D1 or D2. So we have two indecomposable projective bimodules in L1. And similarly, L2, we have two indecomposable projective bimodules which have D2 as their right-hand side. And similarly, J splits into two right cells, R1, where the left side of the indecomposable projective bimodule is D1, and R2, where the left side of the indecomposable projective bimodule is D2. So the left order is given as follows. L1 is left bigger than J1, and L2 is left bigger than J2, and nothing else is left comparable. Similarly, the right order, R1 is right bigger than J1, and R2 is right bigger than J2, and nothing else is comparable. As for the cell modules, so we have four different left cells. For the left cell J1, the underlying category of the cell module is equivalent to vector spaces, on which the object D1 acts as the identity, and all other indecomposable objects in our monoidal category kills this cell module. Similarly, for the cell module corresponding to the left cell J2, the underlying category is vector spaces. The object D2 acts as the identity, while all other indecomposable objects act as 0. and an argument which is similar to the one which we used for projective bimodules over connected self-injective algebras, we see that both cell modules corresponding to the left cells L1 and L2 are equivalent to the natural action of our monoidal category on the category of all projective D plus D modules. And this completes problem 4. Problem 5. Consider the object 2 bullets in the partition category P with parameter delta. Show that this object has the natural structure of a commutative special Frobenius algebra object. Solution. The idea of this solution is to follow the following general fact. Given two algebra objects or two coalgebra objects A and B of a symmetric monoidal category, we can define on their tensor product A tensor B the natural structure of an algebra, respectively coalgebra object. But this is not totally trivial, because when you define multiplication and commultiplication naively, it will not end up in A tensor B tensor A tensor B. It will end up in something like A tensor A tensor B tensor B. So in order to have the commultiplication defined in the correct way, you need to use a symmetric braiding for the middle components. So with this in mind, we just give the following definitions. So first of all, recall the structure maps for our special Frobenius object given by one bullet. So we have the split map as the commultiplication, the merge map as the multiplication, and then this is the unit map and this is the co-unit map. So they are given by these kind of diagrams. So we use this and this symmetric braiding idea to give the following definitions for the object 2 bullets. So we define the structure maps for the object 2 bullets as follows. So we take the structure map for the bullet and then we flip the two middle components in the fourfold tensor product. So this will become our commultiplication, this diagram becomes our multiplication, and for the unit and the co-unit, the diagrams suggest we write them next to each other. So this is our definition, and we need to check the relations. So for the associativity relation is given by the following diagram. So we need to prove that the left-hand side here is equal to the right-hand side here, but we are in the partition category, so in the left-hand side, this point is connected to points 1, 3, and 5, and here this point is connected to 1, 3, and 5. So this part works correctly, and the second part is the same. So in the partition category, this is obvious. And the associativity of the multiplication is just obtained from this by a vertical flip, so it also holds. Next, the co-unitality. So the co-unitality is this diagram, which should be equal just to two straight lines. And this follows directly because, again, for the parts, this point is connected to this one. So these are the empty points. They are just circles without filling. So these are the empty points. So this is connected to this. This gives us the first straight line, and this is connected to this. This is the second straight line. And the unitality is obtained using the vertical flip for the multiplication. Co-commutativity. So if we co-multiply and then use our symmetric braiding, this should give our co-multiplication back. And this is again straightforward. This point is connected to 1 and 3, and here it is connected to 1 and 3. And similarly, this is connected to 2 and 4, and here 2 and 4. So in the partition category, this relation is obvious. Next, we have to discuss the compatibility diagram. So the compatibility diagram is starting from object tensor with itself. We first co-multiply the second component, and then we multiply the first one with the middle. And this should be equal to the composition of first multiplication and then commultiplication. Again, in the partition category, the first point is connected to the first and third upwards and the third downstairs. The first point is connected to the first and the third upstairs and to the third downstairs. And similarly for the other part. So this diagram is also obvious. And finally, the speciality of our object is that commultiplication followed by the multiplication gives the identity. And this is again straightforward. This point is connected only to this one, so this gives us the first straight line. And this point is connected to this one. This is the second straight line. And this completes problem 5. Some questions at the end. Question 1. Check with all details that the first 3 compatibility diagrams in the second part of problem 1 commute. Question 2. Classify all simple finite dimensional modules over the quantum plane. Question 3. Solve an analog of problem 3 in which the matrix X is substituted by the matrix 2X. Question 4. Solve an analog of problem 4 in which the algebra D plus D is substituted by any not necessarily connected algebra A. And finally, question 5. Given two algebra objects A and B of a symmetric monoidal category, show that A tensor B has a natural structure of an algebra object. So this is the claim whose idea we used to treat a special case of certain objects for the partition category. Thank you very much, and that's the end of the course.